Let's keep going with this continuity thing, huh? We got a couple theorems. Throw it in. Not too big. This actually just opens shit up for us. Allows things work a little bit better. Well, here's one. Here's one. So when we want to know about continuity, we want to know where something's continuous. Well, there's these different types of functions. You got polynomials. They're continuous everywhere. Everywhere. A polynomial, here's an example. X to the fourth minus 3x cubed plus x minus 1.7. You know? There's a polynomial. You know, no denominator. All whole numbers. We're good to go. Is the exponents? That shit's continuous everywhere. It doesn't matter. We go to rational functions. That's like fractions and shit. Maybe that, like a rational function. That shit's continuous everywhere except where it's not in its domain, like 2. Right? You can't plug in 2, but it's continuous everywhere. So these functions they're talking about here, a root function. It's continuous. Well, it's kind of funny. It's continuous everywhere it's continuous. It's basically what this theorem's saying. But it's like anywhere in their domains. Do you know your trig functions? This is more of an ominous warning, I think. Actually, more I'm looking at saying, hey, you better know the domain of all this shit. Are you on point with your logarithms and knowing the domains of those functions, that knowing that you're not allowed to have anything but a positive input into your argument? So the argument, the shit you're going to put inside of a log, it needs to be positive. Your input must be greater than 0, not even equal to 0. We don't really use that. We use ln's of x in calculus, but we'll use a little bit of log. But the input's got to be positive. Do you know that shit? Do you know the exponential functions? Things like e to the x. You can plug whatever you want into it. It's continuous everywhere. We have to have this knowledge down. Trig functions. You know all your trig functions and where they're continuous. You know the tangent. Tangent is discontinuous at all odd multiples of pi over 2. Did you know that? There's a lot to learn. That's all I'm saying. It's just there's a ton to go through, and you're responsible for this. I told you that these were, when I came in as a calculus student, I was pretty cool with these. And I guess I was kind of okay with this. But I was not okay with this, this, or this. I didn't know shit about logarithms. I didn't know anything about trigonometry when I walked into a calculus class. And I pulled it off somehow. And I was old. I was in my 30s when I started this shit. So if I can do it, you can do it. So just know this is stuff we got to get down. All right, moving on. Here's a theorem that's going to open shit up. It's going to make things work pretty well. It seems crazy and it's very dense, but let's just run through it. So basically, you're going to throw a function inside of another function. I'm not even going to read this. You go through, you can read this if you want to. Let's look down here. If you have a function trapped inside of another function, you can bring your limit in between the two of them to where the function, you can just take the function of whatever the answer is. And that might seem, you're like, what the hell is he talking about? I got an example. It's saying we're allowed to do this. We've already done it. One of our limit laws actually just gives it to you. Okay. So we look at number 1, and we can actually write this. Our outside function, the purple, is this. It's the square root. There's a root function. Remember back up here? It's like you need to know some shit. Root functions. It's a function. A square root is a function. So what we can do is we can take that limit and bring it inside. So the limit as x tends towards 4 of our x minus 3, 1 plus x. And now we can plug our value in. And we're like, oh, look, there it is. This is the square root of, let's plug our numbers in. 4 minus 3 over 1 plus 3. 4. So we get 1 over 5 underneath a root. So we get 1 over root 5. Hey, if you're one of those that likes to rationalize denominators for numbers, cool, have fun with that. I don't like it much, but I imagine your homework's going to be shitty about it. So 1 over root 5. You ever want to be able to rationalize whatever the denominator that has the root? Multiply top and bottom by it. It's an amazing thing. It just pops straight out. You get root 5 up top. And what's root 5 times root 5? 5. So it's root 5 over 5. I don't give a shit if you rationalize denominators. Calculus, by this point in time, We don't care. We have calculators. There's no need to do that. It's just extra steps, unless it's something that your teacher's beaten into your head. I don't know why. You should know how to, but leaving answers like that, we are not living in the 60s when we didn't have calculators and shit. You know, slide rules. That's where that stuff comes from. Now, this is a good example. You try and plug in 1 into this problem, good luck. I like this problem a lot. It's got so much going on in it. Like, this is the sort of shit I like doing on tests. Because you got to know how to deal with that inside limit. Plus, you got to know what your inverses are, too. You got to know your functional values of your common angles. Typically, I do a big old trig review in a class like this when we're on campus. I would do it on a Friday. I would hold like a 2-hour thing, and I would just teach trigonometry in 2 hours. If people are interested in that, please let me know. But we're going to learn a little bit of trig. You're going to need to know when we get some sort of answer in there, what's cosine inverse of that answer? And what happens when you don't have a calculator? Because a lot of us teachers don't let you have them. I know you're at home and you're like, I'll be able to weasel my way through. But you might end up on campus one day. All right. Let's go. So this is saying we can bring it inside. We're like, let's just take cosine inverse. We're just going to evaluate and bring this limit on in. Okay? So we're going to say it's the limit as x tends to 1 minus the square root of x over 1 minus x. Cool. So now we don't give a shit about this outside. We're like, cosine inverse of, and now we're going to go do some work in there. So maybe you want to pull it away and say, I'm going to work aside. I don't mind writing cosine inverse a few times and just working my way all the way down. Hold on, let me get rid of something. Let me pause. And back. Sorry for the terrible, terrible production value, but I will not fix that. I don't have time. All right. Well, if we look up top, like, hey, look at that thing. 1 minus root x over 1 minus x. What happens if we maybe rationalize that numerator? You know what I mean? Rationalize the numerator. We should have that down. If you're watching this video by now, you should have seen this trick already. Cancels out, and it just equals 1 over 1 plus the square root of x. Cool! There's that magical 1 that we have to get used to. We have to create shit sometimes. It's weird. So we did a little bit of algebra aside, but notice, my equal sign is still following. All right, just how we write things. And now instead of writing in 1 minus root x over 1 minus x, we will now write in 1 over 1 plus root x. Well, shit, now we can just plug it in. Take that 1, pop it in for x, and we get 1 over, so 1 plus the square root of 1. I'm going to move to the right because there's nothing really weird to do here. So it's cosine inverse of 1/2. Y'all got that on point? Hey, in calculus, don't you dare give me degrees. Don't you dare. No degrees. Radians only. Unless it's a word problem talking about degrees. I want all your answers. You ever deal with an inverse? Inverses are angles. They are in radians. So I am not saying that this thing equals 60 degrees. This equals pi over 3. And you got to know the difference between your radians and your degrees. Because radians we can use as lengths. Degrees we cannot. And these are going to pop up in problems, and if you use degrees, you will be wrong. It will not work, so we need to get you the heck away from the idea of degrees and move you into radians if you're not already there.